Alright guys, so Einstein is coming in.
Wait, the real Einstein?
Hey, my name is Michael Scott. I run this lab. My primary area of research is dark energy. I work with some undergraduates in this lab. We look at how dark energy causes the expansion of the universe to accelerate. Normal energy creates positive pressure, while dark energy creates negative pressure. Due to this property, it creates a negative gravity effect, which pushes the universe outward. So for the next few days, I have an Einstein impersonator coming in to teach the students about his life and dark energy, which is a load off my shoulders because my whole dissertation was plagiarized. Alright guys, I'd like to introduce Albert Einstein. He's going to teach you about his life and how he invented gravity.
That's not right.
Okay, well, how he played dice or something.
Warmer.
So my plan for today is to make Dwight believe that the Einstein is the real Einstein.
Hello, everybody. As you know, I'm Albert Einstein. And I thought, since I'm going to be telling you a lot of interesting stuff in the days to come, I might as well start off with a little bit about myself. So, I was born in Ulm, Germany, by Paulina and Hermann Einstein. I'm sorry, is there a problem?
You're boring.
I'm boring.
Yeah. You're not giving us the fun details of your life.
Okay, so what are the fun details?
Well, where do I begin? We all know that you were born in Germany to Pauline and Hermann Einstein. Whoop-de-doo. But after your childhood, you studied physics and mathematics in Switzerland, where you also got your PhD and started working in a patent office. In 1905, it was known as your miracle year because you published 5 theoretical papers that had a huge impact on modern physics. 2 of those were special relativity and the photoelectric effect. And in 1921, you were awarded the Nobel Prize for the photoelectric effect. Because of these papers, you became a world-renowned public figure and became very active in politics. Due to this, when Hitler became Chancellor of Germany, you decided to renounce your citizenship and move to the United States, Princeton, New Jersey exactly, where you decided to live the rest of your life. Am I right?
You know your stuff, Jim. That Pam girl is pretty cute. I think I want to try getting to know her better.
Oh, Albert? No.
I'm pretty sure Jim's messing with me. There's no way that's the real Albert Einstein. I'm like 99% sure. But don't worry, I'll get to the bottom of it.
Everyone, remain calm. Albert Einstein will be a little bit late today.
Can you look at this?
Hold on, buddy. I know you're not the real Albert Einstein.
Yes, I am.
Prove it. How many dimensions are in string theory?
11.
How about superstring theory?
12.
What's the curvature of our space-time?
Relatively flat.
What does E equal?
MC squared, duh.
I'm on to you.
Hello, everybody. So today I'm going to be telling you a little bit about general relativity. So general relativity is a theory I published in 1915, and it explains gravity, basically. So Newton said that two masses are going to be attracted to each other by this force called gravity. But why is it that these two masses come together? And it has to do with how mass interacts with this concept of space-time. So what is space-time? Our notion of space and our notion of time, though they seem different, are actually one big concept called space-time. So really those two things are linked together. A good way to model space-time and how mass interacts with it is with a trampoline. So a trampoline with nothing on it is going to be pretty flat. So if we were to add mass to it, like let's say a bowling ball, something heavy, it would distort the fabric and make this curve. If we now if we now put a small mass, something not that massive, on this indentation, what's going to happen? The marble, or the small mass, is going to fall into the curve coming towards this bigger mass. And this is pretty much what gravity is. Smaller objects following the curvature of space-time that is made by these bigger objects. And if we go from a top-down view now, this is the massive object and this is the bounds of the trampoline. If we were to throw the marble with the correct velocity, we could get it to come in and then go around in the curve, which makes an orbit. So that's pretty much how we can describe space and the universe in order to account for this gravity. Hey, Pam, is it? Mind if I explore your space-time curvature?
I once learned a lot from this Albert guy. Who knew he knowed so much?
Michael, we need to talk about this Albert Einstein guy. He's no help to us. I could explain this stuff better than he could. He hasn't even talked about his theory of special relativity.
Alright, explain it to me then. Make it quick.
Okay. So the theory goes, for objects that are moving, mass will increase, time will increase or slow down, and most importantly, distances will decrease. So to put this in perspective, let's say there's a rocket ship hurtling towards Earth. Someone on Earth will see the rocket ship coming towards it. However, it'll seem squished compared to if you were on the rocket ship. So if you're on the rocket ship, and you're hurtling towards Earth, the Earth will seem like it's squished. This means that all distances we see aren't objective, and that when we're dealing with a moving object, it's important to know, because everything is moving in relative to each other.
I didn't understand a single word you just said.
I still don't believe that's the real Albert Einstein. I mean, he hasn't even told us about his theory of special relativity.
Why would he? That would give away his secret of time traveling.
According to that theory, you can only time travel in the future.
Maybe he did go to the future and learn more stuff and then learned how to come back. You never know.
Unfortunately, today is Albert's last day before he has to go back.
I've seen Dwight research Einstein. He's been asking about Einstein to other people. He's been losing sleep. I think he believes that this is the real Einstein.
Alright everybody, so I'm going to finish my talks with something big and exciting. I'm going to be talking about dark matter and dark energy. So out of all the things in our universe, we estimate that 5% is the matter we know. So really, we only know things about 5% of our universe. 27% of the unknown part is contributed by dark matter, and then the last approximately 68% is dark energy. So if we don't know what dark matter and dark energy is, then how do we even know that it's a thing? And how do we get these numbers even? So let's start with dark matter. How do we know that dark matter is there? There are two methods. So the first method relies on close galaxies. So if we have big, massive galaxies that are relatively close to Earth, we can use big, bright, distant galaxies or quasars. So the big, bright galaxies and quasars are going to be producing light. And these big close galaxy clusters are going to use or are going to distort space-time in such a way that the light from the distant galaxy or quasar bends around it and reaches Earth. So this galaxy, the close nearby galaxy or cluster, is going to distort the light in a certain way. And we can measure indirectly how much mass or how massive this close galaxy would be with how much it's distorting, how much it's lensing, it's using gravitational lensing to distort the light. And then we can compare that number, the indirect number, with an experimental number of being able to actually visibly calculate how much mass we see in that cluster. So the visible mass is less than the theory mass. Much, much less, actually, in a lot of cases. So why is it that we see a lot less mass than we've noticed? And it's because of dark matter. Dark matter is a thing that we can't see, that doesn't even interact with itself or normal matter, but it has effects of gravity. So with indirect methods, we can calculate how much dark matter should be in close nearby galaxies and clusters. But what about distant ones? For distant galaxies, we can use the fact that small dwarf galaxies should be disrupted by larger galaxies due to the larger gravitational pull. But if we notice that a dwarf galaxy isn't getting disrupted due to the larger galaxies, we can calculate the minimum amount of mass needed to have this dwarf galaxy be sustained and uninterrupted. And then we can again use visual means in order to determine how much mass we actually see, how much normal mass is actually in there. And again, if the mass that should be in there is more than how much we actually see is in there, that means that we have dark matter. So that's how we can test and notice the effects of dark matter. Next, dark energy. So, what is dark energy and why do we think it's a thing? So this comes from the fact that the universe, as we know it, is not accelerating inwards. We would think that gravity is causing all of the universe to come inwards. But we know that that is not true. We can see through cosmological redshift that the universe is still expanding and not and it's actually expanding at an accelerated rate. That means that something is pushing the universe outwards. And we believe that dark energy is the cause of this repulsion. You know what you remind me of? Exotic matter. Because you're exotic and you matter to me.